Okay, so the purpose of this little video is to go through the review problem step by step. Some of you may not need that, and so I also posted just the answer key. Um, if you are using this, go ahead and jump ahead to the problem you have questions on. If it's still not clear what you need to do, please contact me. Once you're done with this review and you're satisfied that you are feeling comfortable, then go ahead and take the online assessment. We're going to be doing all assessments for the remainder of the year, open book. So feel free to use your notes and do the best you can. Okay, so the instructions for this problem are to graph the parent function and then graph the transformation. And so here we have the function y equals x squared, the parent quadratic. And so we're going to quickly graph that function, and then we'll talk about how we're going to transform it. So a quadratic, of course, is a parabola. And so we're going to graph the points. We have 0, 0. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. And then we also have the corresponding symmetric points across the axis of symmetry, which is the line x equals 0, or the y-axis. So here's our y equals x squared graph. I'm going to draw it as best I can here on the computer. All right, so that looks as good as it's going to get. And so what's going to happen when I do this transformation that they ask us to do? Well, the transformation graph is going to be f of x, and you can see that inside the function to the input, I'm subtracting 3. So this is going to be x minus 3 squared, and then plus 2. So there's two things that are happening. This minus 3 on the inside is shifting this graph 3 units to the right. The plus 2 is shifting it up 2 units. So I'm going to start with the vertex, and it was 0, 0. Well, actually, why don't we use the right color here? So if I have 0, 0, and then I had 1, 1, and then I had 2, 4, and then 3, 9. So what's going to happen to those points? Well, each of the points on the graph, I do not need to make a list like I just did. You could just do it graphically. I know that each of the original points is going to be moved 3 units to the right and 2 up. So, for example, this point right here, the point 2, 4, I know that's going to go 3 units to the right and 2 up. So my new spot is going to be here. But alternatively, you could do it point by point. So I'm adding 3 to each of the inputs. So this is going to be 3 plus 0, 3 plus 1, 3 plus 2, 3 plus 3. And for the outputs, we're going to be adding 2. So the original vertex is 0, 0, so that's now going to be 3, 2. And 1, 1 has become 4, 3. And 2, 4 is now 5, 6. And 3, 9 is now 6, 11. And of course, that last point I'm not going to be able to graph on this particular grid. So let's go ahead and graph these points. And so we have 3, 2, and 4, 3, and then 5, 6, which we've already graphed, and 6, 11, which is off the graph. So I'm going to do the symmetric points across the axis of symmetry, which is now the line x equals 3. So we have this point right here and this point right here. And so if I draw that graph, there's my new parabola. So the shape did not change. It's not stretched or compressed, but it is the exact same parent graph shifted 3 units to the right and 2 units up. Okay, so the parent function y equals x. So the very first thing we want to do is to graph the parent function. And so remember, absolute value is the distance from 0. So it's going to be removing any negative signs, but if your input is positive, it stays positive. So if I had, as an example, -3, I would have 3 for my output, an input in -2 would give me 2, -1, 1, 0, 0, 1, 1, 2, 2, 3, 3. And what this in fact does is it makes a graph with a sharp V shape, and sometimes it's nice to think of it as a piecewise function with the part in quadrant 1 having a slope of 1 and the part in quadrant 2 having a slope of -1. And so we have this nice V-shaped graph. Now, when we do this transformation that we're thinking about, we're going to be multiplying it by a half. And those slopes are going to change from 1 and -1 to 1/2 and -1/2. Also, we can see that we're subtracting 5 from the output, so the vertex in the entire graph is going to be shifted down 5 units. And so my new equation is going to be f of x equals 1/2 absolute value of x minus 5. So two things are happening here. We have a vertical compression, and we're shifted down 5 units. And so we're going to start at 0, -5, because the original vertex, which was 0, 0, has been shifted so that we're now at 0, -5. And then instead of going up 1 over 1, we're going to go up 1 over 2, because that slope has changed from 1 to 1/2. So here it is. And then on the other side of the graph, we're going down 1 over 2. And so here we are, down 1 over 2. And there's our transformed graph. And all right, the third example we're looking at is a parent function, which is the square root function. And remember, square roots, if we're sticking to the real numbers, we cannot have any negative inputs. And so this is only defined for a domain of greater than or equal to 0. So although we can take square roots of numbers like 3 and 2, they're not going to give us nice outputs to graph. So we're going to make a sketch of this graph by using inputs of 0, 4, and 9. Because if I have the square root of 0, I get 0, square root of 4 is 2, square root of 9 is 3. And so that's enough to get a decent sketch of what this graph would look like. And so you get this curve like that. And what we're transforming this to make actually by multiplying the output by -1. So the transform graph, which is going to be f of x equals minus the square root of x, is going to reflect this over the x-axis. So it's going to reflect it like a mirror over this x-axis. If we were looking at the table, we could use the table to do this as well. We are going to have the inputs are not going to change. We're still going to, nothing's happening inside the function. So we have 0, 4, and 9, but the outputs are going to change signs. So when I put in 0, I'm still going to get 0, but when I put in 4 now, I'm going to get -2 instead of 2. When I put in 9, I'm going to get -3. And so we have these points, we'll have 0, 0, but we're going to have 4, -2, and we'll have 9, -3. And so we have this upside down version of the previous curve. 3 units. Okay, so the next parent function is another parabola, and we're going to transform it by doubling the output and subtracting 3. And so our transformation equation is going to be f of x equals 2x squared minus 3. So let's graph the original, the parent function. So we have 0, 0, 1, 1, 2, 4, 3, 9. And then the matching symmetrical points across the axis of symmetry, which is the y-axis. And here's our original. That is not good enough. Let's try this again. All right, still not perfect, but it's as good as we're going to get. All right, so what do we expect to see change when we graph this transformation? Well, the -3 tells us it's going to move down 3 places, and the fact that I'm multiplying by 2 means that the graph is going to get stretched and be thinner. It's going to change faster than the original. And so let's just take some points and see what happens to them under the transformation. So if I do 0, 0, I'm going to see the 0 does not change. The input's not going to change. My output 0, though, I'm going to double it. 2 times 0 is 0, and subtract 3. So my new vertex is at 0 minus 3, right here. Then the 0.11 in the original parent graph, again, the input's not going to change, but my output of 1, I'm going to double it, 2, and then subtract 3, and I'm going to have 1, negative 1. Then I had the 0.24 in the original graph. Again, the 2 is not going to change because nothing's happening to the x. But my output of 4, I'm going to double it for 8, and I'm going to subtract 3, and so I'm going to have 2, 5. Then for 3, 9 in the original graph, I'm going to have 3, and then 9 times 2 is 18 minus 3, so that's 15. And that is not going to be, it will not fit on this grid. So I'm only going to be able to graph the 3 points that I have here. And then I'm going to match the axis of symmetry did not change, so I'm going to draw the symmetrical points across the axis and then see if I can sketch in the graph. Okay, so we can see that it shifted down and it also got thinner. So question 5 just asks you to discuss what's happening when I transform this function, a quadratic, and x squared is turning into a times x minus h squared plus k. Well, there's several things that happen. One is that, and it's probably easier to talk about each of them separately, so why don't we start with k. So if k is a positive number and I add it, I'm going to be shifting up k units. If k happens to be less than 0, then I'm going to be subtracting k, so I'm shifting down k units. Right? Similarly for h, if k happens to, or I mean if h happens to be greater than 0, in this case, I'm going to be subtracting a positive number, so it would be something like x minus 3 squared. Well, that we know moves in the opposite direction you would expect, so that's going to be shifting to the right h units. On the other hand, if h is a negative number, if it's less than 0, then I'm going to have x minus a negative, so then it's going to be plus, and so then it's going to be shifting left h units. And then the last one, if we talk about a, there's a couple things. One, if a is greater than 0, it's going to be concave up. If a is less than 0, it's going to be concave down. But you should also be thinking about if the absolute value of a, whether it's positive or negative doesn't matter, if it's greater than 1, then you're going to be thinner than the original. And if that's a vertical stretch. And if the absolute value of a is less than 1, then it's going to be fatter than the original. So those are the things that would make up a complete answer as you talk about problem 5. So problem 6 wants you to describe each thing that's happening with these functions. And so let's talk about part A. So x squared is being transformed so that it is now x plus 7 squared. So one thing that's going to happen is it's shifted 7 units to the left horizontally. We also see that we're subtracting 10 afterwards, so it's shifted 10 units down. And then the other thing that we see is that it's multiplied by 3, so it's concave up, but stretched vertically by a factor of 3. All right, let's talk about B. So B, we're talking about the square root of x. And what do we see that's happening? Well, first of all, inside the function, I can see that it's x plus 8 now. So this is going to be shifted 8 units to the left horizontally. We can see that it is plus 17 outside the function, so it's going to be shifted 17 units up vertically. And we also have a factor of minus 5, so it's reflected over the x-axis. It's upside down, and it is also stretched by a factor of 5. Vertically. So those are the things that are happening in that transformation. So here we have an absolute value graph, and I put it into my graphing calculator, and I can't see anything when I try and graph it. Why might that be? Well, the short answer is that the standard window is going from negative 10 to 10. So it's not suitable for this function. And why not? Well, I can see by looking at this that my vertex is going to be at 102, 5060. So clearly that's not going to show up on a negative 10 to 10 window. So if I do want to adjust this so I can see it, I'm going to start by looking at the vertex, and I'm going to say, okay, 102. So I'm going to need to center my domain around that 102 vertex. So maybe I go negative 200 to 500 as a start. And then for my y-axis, I have to get 5060 there, but because it's inverted, it's going down. I don't have to get much above 5060. So maybe I set my y maximum to 5100. And then my y minimum, it says a complete graph, so I do want to see my x-intercept. So I might start by saying just negative 10. And I put that in, and what I'm going to see is I'm going to see that I have a graph, something like this, where I can see this. So I see my vertex, I can see the shape of the graph, I can see that where it crosses the y axis, but I don't see where the zeros are. I don't see where it crosses the x-axis. So I'm going to have to do some further adjustment of the x-axis. And you can just play with that x window once you have that. And so I found that after playing with it a little bit, that a suitable window might be my domain might go from negative 2500 to 5000. And my range would be something from negative 10 to 5200. There's lots of other windows that would also work. But this would give me a complete graph. If I use this window, I can see where my function crosses the y-axis, the x-axis, and I can see where the vertex as well. So here I have a graph that it's piecewise defined, but I'm just going to use the graph in my knowledge of transformations to graph the transformation graph. And so what's going to happen here is I'm going to take these points that I have in the original graph, and I'm going to transform them using the transformation rule. So there's no single equation I could write for this. I could write a piecewise graph, but that would be more work than I want to do. So let's look at x, f of x. And what does this graph look like? Well, I have these following points. I have -8, -1. I have -2, 2. I have 3, 2. And I have the point 5, 6. And I'm going to transform this graph by doing two things. One, I'm going to invert it, and then I'm going to add 3 to it. So this graph is going to be flipped over the x-axis and then shifted up by 3 units. And so we're going to have our new function is going to be g of x. And so we're going to have the inputs do not change. We have -8, -2, 3, and 5. Those are the critical points where it turns. And then we're going to take the outputs and do the transformation to them. So we can see that the output for -8 is -1. So I'm going to do the opposite of -1, which is 1, and then add 3. So I'm going to have -8, 4. The output for -2 is 2 in the original function. And so I'm going to do the opposite of 2, which is -2, and add 3. So my new output for g of x will be 1. And similarly for the inputs of 3 and 5, I'm going to have -2 plus 3 for the input of 3. And so that would be 1 also. And for the output of 6 at 5, I'm going to have the opposite of 6, which would be -6 plus 3, and that would give me -3. So let's graph these on our graph. So we're going to have -8, 4. So 1, 2, 3, 4, there we are. And we will have -2, 1, and 3, 1. So -2, 1, and 3, 1. And then we have 5, -3. And there we are. And so when we connect these, this will be our new function g of x. And actually those, I wonder if I can make that a little better connections. So let's see here. Let's draw carefully. All right. So as you can see from my graphs that I'm doing on technology, is that it's a little bit challenging to draw some of these connections. I hope I get better at it as we practice together. So there's our transformed graph. So many people in this country are tied to a social security number, and in this problem, we're just assuming that there's some kind of database somewhere where you would input your social security number, and this function in the computer, f of x, is going to take that input and it's going to output the year you were born, your birth year. So what would happen if somebody was messing with that database and they made some errors? So the first one, the function is going to change so that it's, instead of f of x, it's f of x plus 10. So what would happen? What kind of answer would you get? So if my social security number, which it's not, but if my social security number was 568327510, if I put that into that computer program, the first thing it's going to do is add 10 to that. And so then it's going to give me 568327520. It's going to look up the birth year, and then the birth year that would come out would be for that different social security number. So let's say I was born in 1995. Well, this new person, maybe they were born in 1960. Okay. Actually, the number's later than that, so I'm guessing that it probably would be earlier. Let's say instead of 1960, let's say they were born in in 2000. Okay, so maybe this would be for 2000. I know they're not; these numbers are not necessarily sequential, but um, let's assume that. All right, so you would get the wrong year because you would be getting someone else's year of birth. All right. The second example. So here we have a function. It's going to input your social security number. So I input 568327510, and it's going to calculate my year of birth, which was 1995, and then it's going to subtract 5. So what it's going to report out is that I was born in 1990. The last example is it's going to I'm going to input my social security number 568327510, and it's going to calculate my year of birth 1995, or not, or look it up, probably not calculate, and then it's going to double it. So it's going to double it, and it's going to report out that I was born in 3990. Okay. So those are 3 different kinds of errors that could happen. And what I want you to notice, if you think about those, which one of those 3 would be easiest to catch? Because there are lots of errors that happen in databases. Sometimes the errors are obvious, and sometimes they're not obvious. And the ones that are obvious are the ones that people are aware of, and they can fix them. The ones that are hidden away, sometimes they persist and they never get corrected.